Hello, my name is Jeffrey, and this is my video lab report for Physics 2211M, lab number 5. To introduce this lab, let's first analyze its purpose, its models and fundamental principles, and the main result. The purpose of the lab is to determine the optimal angle for Tarzan swinging from a vine off a tree branch using to travel the greatest distance using given variables. This is done by applying the momentum principle, the energy principle, and kinematics. Since Tarzan is subject to the force of gravity, it will be useful to understand the momentum principle. F net equals ma equals m delta v over delta t equals delta p over delta t. Additionally, since Tarzan's motion will be modeled in 2 dimensions for his lab, kinematics can be applied. Specifically, the kinematics equation used is y final equals y initial plus v initial in the y direction times delta t plus 1/2 g times delta t squared. An intermediate step for finding Tarzan's optimal launch angle will be determining his velocity at certain points in his swing, which will be done using the energy principle. Delta E system equals work done by surroundings. Furthermore, the forces exerted on the mass can be modeled using a free body diagram. However, in this case, the only force acting on the mass, Tarzan, while he is in the air, is the gravity. Using the momentum principle, the energy principle, and kinematics, an equation was found relating the travel range to Tarzan's launch angle. A glow square program was developed to calculate the optimal launch angle, given the velocity at the bottom of Tarzan's swing, the branch height, and the length of the vine. Here is a visual model of Tarzan's scenario. The diagram reveals several given constraints, or constants. M equals the mass of Tarzan, V equals Tarzan's velocity at the lowest point of his swing, V naught is Tarzan's velocity when he lets go of the vine, H is the elevation of the branch, theta is the launch angle, R is the horizontal distance traveled or the range, and this can be split into R1, which is the horizontal distance traveled while contacting the rope, and R2, the horizontal distance traveled while he is experiencing projectile motion. Here, the system is Tarzan, and the surroundings are the vine, tree branch, and the earth. However, there will be an exception when we use the energy principle, which will be discussed later. In part 1, the task was to derive the formula for the range of a projectile as a function of v naught, theta, and g, assuming the projectile lands at the same initial height, i.e. h equals 0. Using the kinematic equation for displacement in the y direction, delta y, I solve for time in the air. Delta y equals 0 because the initial height and final height are the same. Then I substituted for the time into the definition for velocity. These calculations are shown to the right. For part 2, the task was, starting from a height capital H, determine the horizontal range to r sub 2, given an initial velocity v naught and an angle theta. Once again, I use the kinematic equation. H is the sum of the height of the tree branch and the vertical displacement from swinging on the vine, so delta y equals negative h. I isolated delta t using the quadratic formula, and then substituted it into the definition for velocity once again. For part 3, the task was simply to confirm that as h approaches 0, your equation would reduce the equation derived in part 1 for level ground. As it turns out, taking the limit of the equation derived in part 2 yields the limit equation that was found in part 1. For part 4, the task was to use the energy principle to determine V naught in terms of V, G, L, and theta. The system here is now redefined to be Tarzan, vine, and earth, and the surroundings are nothing. This is done to make the work done by the surroundings equal to 0. The initial condition is the lowest point of the swing, and the final condition is the highest point of the swing, right when Tarzan releases the vine. Here, the only changing energies are Tarzan's kinetic and potential energy, and these calculations are once again shown to the right. In part 5, the task was, if R total equals R1 plus R2, derive a formula for R total in terms of V, L, theta, G, and H. R1 equals L sine theta using trigonometry, and R2 equals V naught cosine theta delta t according to the definition of velocity in the x direction, as calculated in part 2. I substituted these values into the given equation first, and then substituted unknown variables from where the equations derived in the previous parts. The final equation turns out to be pretty lengthy. Now for the computational model code, this was created in order to make it so I didn't have to calculate the optimal angle using every single whole number degree. So the computational model creates a graph, range plot, and then creates a slope on the graph, range curve. It also defines VHL launch angle, optimal angle, and R max, as well as G, the gravitational constant. The calculation loop itself tests every launch angle from 0 to 90 degrees. First, it converts the launch angle to radians, as that is what GlowScript accepts for trigonometric functions. Next, the loop defines V naught, delta t, R1, and R2 according to the equations derived in parts 2, 4, and 5 in the calculations. Although I could use the equation found at the end of part 5 instead, I decided to use these intermediate values to make debugging easier and to make the code easier to read. With all the intermediate variables defined, the loop then sums R1 and R2 to R total, as given in part 5 of the calculations, and prints R total to the console. If R total is greater than the variable R max, the loop then replaces R max with R total and stores the launch angle from that iteration as the optimal angle. Finally, the loop updates the graph, increments the launch angle by 1, and advances to the next iteration. At the end, the program prints the initial conditions and reveals the optimal angle. This is what the output of the program looks like. Note again that this is not a graph of Tarzan's optimal trajectory, but rather different launch angles and the horizontal distance they would place Tarzan at. The peak of the curve represents the most optimal angle, which is printed to the console for clarity. For this lab, there are not any possible sources of error for the observation data, as this portion was replaced with the calculations. However, there are some sources of error for the computational model, namely only testing launch angles with whole number degrees and rounding variables in the calculation loop. How does the launch angle vary with the tree branch height? Lower tree branch height correlates with greater optimal launch angle and vice versa. For example, if h equals 1 meter, the optimal angle is 37 degrees as shown at the top, and if h equals 100 meters, the optimal angle is 10 degrees. Now, what if Tarzan was carrying Jane with him? Here, mass gets cancelled out in the kinematics equation. Therefore, Tarzan can use his hands to carry Jane and swing on the vine by clenching his ass cheeks without impacting the optimal launch angle or range.